In this video, I wanted to introduce you to the Chronodot real-time clock modules made by a company called Macetech. Before I start, I should point out that this video is not sponsored by Macetech or anyone else for that matter. These modules are just out of my stock that I use for various projects. The Macetech Chronodot 2.1 here has been around for years. It's based on the Dallas, then Maxim, now Analog Devices, DS, as in Dallas, 3231 SN, Sierra November, clock chip, real-time clock chip, which you'll see in a second. That chip's been around for probably something on the order of 15 years. And just to pull this off, this is what the chip looks like on the back. It's again, what's really amazing about this chip is that it has built into it a 32.768 kilohertz crystal, as well as a temperature measurement and temperature compensation built in and automatic. And what this really means in practice is that this chip is accurate enough to be able to, and stated to maintain about 2.5 parts per million accuracy. And to put that in perspective, 2.5 parts per million equates to not losing or gaining about 90 seconds every year. In practice, though, I found that these maintain actually somewhat better accuracy than even that. So these have certainly been probably the premier real-time clock chip to use because it's relatively inexpensive and just does a fantastic job. And it's been what Macetech has chosen in the past for many, many years for their Chronodot series of real-time clock modules. The other thing you'll notice is obviously the module is battery backed. There's a CR1632 lithium cell in this holder. Also up here in front, you'll notice there are a couple of resistors that I installed. These are pull-up resistors for the I2C, SDL, and SCA lines, and these are necessary for I2C to run properly. These are optional. The Chronodot provided spots to mount these resistors I did here in case they were not elsewhere within your circuitry. If they are elsewhere in your circuitry, you didn't need to mount these resistors. So somewhere along the I2C chain, you would have pull-up resistors of some kind. Apart from that, it's breadboard friendly, and it's on a breadboard for a reason that you'll see very shortly. So it's on 0.1 centers, and it's 2 rows of 4-pin headers on which they bring, well, obviously they bring out power. You put power and ground, and brings out SCL, SDA for I2C, a couple other things, as well as the 32 kilohertz output, as well as an output called SQW, which is you can optionally set it to output a rather accurate signal of 1 hertz, 1 hertz, or 1024 hertz, or 8192 hertz, or 496 hertz. So you can do that programmatically. I usually set the SQW output to output 1 hertz, or 1 pulse per second. The 32 kilohertz outputs the 32768, which is temperature compensated. So you can watch that on a scope or use it for some other purpose. Recently, meaning in 2022, Macetech rolled a new version of the Chronodot, and in the form of the Chronodot 3.0. And I'm going to mount it on the breadboard here, right below its predecessor, and you'll see why in a minute. The most obvious thing that they did is they kept the diameter the same of the module, but they chopped off the sides. And the reason they did this is because if you notice, and the reason I put it on the breadboard is the pins are here, so they're plugged into this row, as is the Chronodot 3.0. But because the thing is round, this over here, it hides or overlaps the next row of pins over, and this made it hard to use that row of pins to actually access to access the signals on these pins. And so that's why they simply removed a bit of PC board issue to uncover this row of pins, so you could use and plug into them. The other obvious difference is the battery holder. This was a side load, if you will, CR1632 lithium cell holder. I didn't really care for these, and I guess neither did Macetech. One reason is if you choose to solder this to your circuit, if you solder the entire Chronodot into your circuitry, you're going to find it pretty difficult to remove the battery. So what they did is they traded a side load for a top load battery holder, and in the very, very unlikely event you would need to change the battery ever, you can simply pop it out by releasing the catch. And you're probably never going to have to change the battery, because when powered off and in battery backup mode, the RTC chip uses a ridiculously small amount of current. And obviously when powered in normal operation, it uses no current, so it's equivalent to the shelf life of the battery. I'm going to take these off their breadboard so we can look underneath them. If we look underneath, we see, in the case of the Chronodot 2.1, we see the DS3231 here, which is in a small 16-pin. It is a dip, but it's a small outline surface mount dip. So it's 16 pins, but half the size of a traditional dual inline package. And again, this has been in this form factor for, again, I'm looking at something like 15 years, and it's been a great real-time clock chip. Clearly, they changed chips. So Macetech went from the DS3231 at some point last year to roll the Chronodot 3.0, which uses not the Dallas or DS3231, but a new successor chip, if you will, released by Analog Devices, called the MAX31328, and that's this little chip here. Notice it's ridiculously small. It's called a LAN grid array chip, and it's 5 millimeters on a side. It's truly a tiny surface mount chip, but it is in every way register compatible with the old DS3231. It's functionally compatible. It's output and input compatible. It's essentially a successor to the chip. Personally, Maxim doesn't talk about this, but I suspect that they had to roll a completely new die and internal arrangement of this to fit whatever oscillator they're using with its temperature compensation and new die into this truly tiny LGA package. If you recall, the pull-up resistors that I installed here no longer necessary here, because Macetech helpfully included the I2C pull-up resistors here and here. And if you don't need them, you can simply cut these traces, which disables them. Finally, because they had room on the new Chronodot, Macetech added a 24C16, which is a 2K by 8 byte, so a 2 kilobyte serial I2C non-volatile double EEPROM. And the functionality, this sits on the I2C bus along with the RTC chip, but apart from that, they're totally separate. In other words, they have nothing to do with each other logically. You're free to use one or the other or both as you see fit. One peculiarity of the 24C16 is it is a 2K by 8 chip, but internally it's organized effectively as 8 256 byte segments. And in fact, each of these 8 256 byte segments appears to the I2C bus as a separate I2C device with a separate I2C address. So this actually occupies hex addresses 50 through 57. apart from that, it's entirely usable, and it's actually pretty simple to using the wire library or whatever you're using for I2C to address, read, and write this chip. Just as it's actually been very easy to read and write the registers inside the actual RTC chips. So in a nutshell, that's really the differences between Macetech's existing Chronodot, previous, I should say, Chronodot 2.1, and their new Chronodot 3.0, which, and both are easily available through Macetech or any one of their distributors. So here's my little test setup that I use to check DS3231s with a scope and just for functionality. It's pretty simple. Arduino Uno clone, in this case a Chronodot 2.1, which is DS3231 SN based, and over here an OLED display. Here's the Chronodot 3.0 awaiting to be plugged in. The wiring is ridiculously simple. By the way, this is a 5-volt, one of those 5-volt buck converters, simply to power whatever's on the breadboard, so I don't have to use the Arduino Uno's 5-volt regulator to do that. Apart from power and ground, the only wiring here is the I2C, SDA, and SCL lines, which go into this module, and then they go on out in parallel, go on out to the OLED display, because that's all that's necessary to run both parts. In addition, from the DS3231 module, I bring out two signals, which I pull up with these two resistors because I need pull-ups. One is the SQW signal, which I typically set to output 1 Hertz, and then I run that into pin 2 of the Arduino, and I set that up as an interrupt, so the Arduino gets interrupted once a second, I believe on the falling edge of this, and it simply uses that interrupt to read the time out of the registers of the DS3231 and sets a flag so the main loop can then go and display it on the OLED. And that's really all this particular sketch is doing. I wanted to show that basically that's it. The 32 kilohertz output I'm not using right now, but typically I throw this onto a scope because that's what I use that as a telltale sign of good versus bad chips. I wanted to just show the Chronodot 3.0 as well running here, and to do that I'm going to be kind of brave, and I'm going to pull out the Chronodot 2.0 with the power on, and the script goes a little haywire, and then I'm going to plug in very carefully the Chronodot 3.0. Obviously this should be done with the power off, but I'm being reckless. I'm just making sure to line up the pins correctly so I don't fry the module. And ooh, look, without even resetting, the sketch picks up, rereads, and treats the Chronodot 3.0 identically. Now I'll keep in mind both of these have obviously been initialized with the date and time and synced up, and so that's why the time is correct. And obviously their batteries have been in place for quite some time. So that's just the difference between the Chronodot 2.1, which is running the DS3231 chip, which you can see here, and the Chronodot 3.0 from Macetech, which is running the MAX31328 which is this tiny little chip here in the middle. And that's it. So we've hooked up the Chronodot to our Arduino. In particular, we've also hooked up the I2C, SCL, and SDA lines to it, and we've loaded up our I2C scanner sketch, which will scan every possible I2C address on its bus and tell us what it finds. So let's run it. And it finds a whole bunch of stuff. Okay, so first and foremost, at hex address 0hex68, we find our 31328 RTC chip, which is fortunately what we'd expect. That is the same exact address as a DS3231. But then we find 8 devices starting at hex 50 to hex 57. That obviously has something to do with the 24C16 2K memory. But why 8 I2C addresses respond? I would have just expected, frankly, hex 57 or maybe hex 50 to respond, and then I could address anything in the 2K address space. Turns out the 24C16 is a little bit strange. It actually deliberately responds to all 8 of the addresses and splits its 2K byte address space into 8 half K, quarter K, 256 byte segments, and each one of those responds to a different address, OX50 through OX57. Fortunately, the 24C16, you don't have to hardwire any of these addresses. It always responds to these 8 addresses, and you build in the 3 least significant bits of this, 0 through 7, into the address that you're looking for when you address the chip in the I2C protocol, and then in the address field of the data that you send it, you put in the remaining 256 or 8 bits of address. So it all works pretty seamlessly. So now we're ready to actually test our little 24C16.